So I'll say some general features of electric kilns. Most of them, and this is sort of, and I'll point out some, this is where some of these differ from wood-fired kilns or gas kilns. Almost all electric kilns are single chamber. You know, we talked about if you're familiar with gas kilns, especially wood kilns, you can have multiple chambers, like the climbing kilns of Japan. We have the Noborigama, and one chamber connects to another chamber, connects to another chamber. Electric kilns are basically a single chamber. You don't have multiple chambers. And they're all basically some kind of box with a metal frame. If you notice, you don't see arch designs with electric kilns. They're all basically some kind of a box. One of the reasons is because they're for indoor use. You really can't have electric kilns sitting in, not very practical, in an unprotected shed or an unprotected facility outside. They need to be protected. And as I mentioned before, the size of the box or the size of the kiln is limited. They can be long, but you can't make, it wouldn't be practical to make an electric kiln as big as this room for production. That's why they go to tunnel kilns or something, rather than just making bigger and bigger boxes. And the elements, in all cases, the elements are located on the walls, the elements, because they have to hang them somewhere. So the elements hang on the outside to keep the inside open to fill up with the wear. And also the other thing with the more modern ones, they're all very well insulated. They may be with did you all see the insulating fire brick and see the difference in the weight? And as you can imagine, along with the weight, the brick is a lot better insulating, the lightweight brick, than the heavy brick. And the blanket is even, again, is a lot better insulator than the brick, even the lightweight brick. So a lot of at least in industrial kilns, a lot of the kilns now are lined with blanket. They might use brick for the outside, like a shell, or even metal, and they're just lined with the blanket. The blanket is not practical for the kilns that we use because it's too easily damaged. After it's fired, it gets, you notice that this is nice and flexible. It is kind of like a blanket. But after you fire it a few times, it gets brittle. So if you bump it, pieces fall out of it. So you have to be very careful. It's not suitable for schools or really for the kind of pottery studios, the pottery kilns that we use. The bricks are sort of the best compromise. They're not the best insulation, but they're a little more durable.
What is it about the light brick that's so much makes it so much better than that heavy one?
The air hole. You know what the single best insulating material is? Air, okay. Space. And so it's the fact that it's full. You know, this is why, you know, what's the insulating, you know, the fall, everybody wears in the fall, like the fuzzy fleece. Yeah, fleece. The reason why fleece is a good insulator is because all the air that's trapped in it. So it's all the little air pockets in there that actually provide the insulation. The same way in the blanket, only in the blanket, the air pocket, there are a lot more of the pockets and they're a lot smaller. And so the smaller and smaller you can make the air pockets and the more you have, the better insulated. So it's the air that's doing the insulating. The other thing about electric kilns that, at least for the small models we use, they're not owner built. You know, people build their own gas kilns. We're going to build one out here. People build their own wind kilns. Most people nowadays don't build their own electric kiln. You could. I knew a guy that built one in Maine because he had a supply. He could get some elements cheap, and he just thought it would be fun, and he almost burned his house down. But it was fun. So you could. But whereas industrial, and so they're commercial products. And then, whereas industrial kilns are custom built, they'll literally come in and build it on site. But again, it's constructed on site. It's not they don't show up with a truck and drop it off. They build it on the site. So that's another difference between gas and wood, is that people generally don't build their own. The last thing is there are three major components when we talked before about the other kinds of kilns, wood kilns, gas kilns. Three sort of parts of a kiln. There's the heat source, the wear chamber, and the chimney. And this is true of wood kilns and true of gas kilns. Well, in an electric kiln, the heat source and the wear chamber are combined. We don't have a separate combustion chamber. Like in a wood kiln, you have the combustion chamber or the firebox, and then you have the wear chamber, and that's also true in a gas kiln. You don't have that in electric kiln. You have just the one chamber. That is the heating chamber and the wear chamber. And you don't need a chimney. Now, you may need some kind of a vent to get the fumes out of it, like if it's indoors, you may need a vent to get the fumes out of the building or something like that, but you don't need a chimney. So it's different in terms, you still have those three parts, the heat source, the wear chamber, and some kind of a vent, but they're combined or they're used differently than they would in the wood and the gas and the gas kilns. In terms of principles of operation, basically, it's pretty simple with electric kiln. If you control the electric power, you control the heat. The more power you put to the elements, the longer or the hotter the elements get, and the more heat you get. Pretty simple. But as I mentioned before, one of the big differences, there are no longer flowing gases moving through the kiln. When you're heating with a wood kiln or with a gas kiln, you've got essentially a river of hot gases that's moving through the kiln and bringing the heat to all the pots. You don't have that any longer. You've got essentially stagnant air in the kiln. Almost all the heating is done by radiation. That's the heat is being radiated from these glowing elements that are on the walls. And so one of the differences is it's a direct line. It can be blocked. If I have a big pot sitting on the outside of a shelf next to the element, then the little pot that's sitting behind it won't get hot until the big pot gets hot, and the big pot heats the little pot. Because if it can't see, if the radiation from the element can't see or hit directly that little pot, the only way the little pot can get hot is by something next to it getting hot. So electric kilns heat the ware by the work on the outside gets hot, which makes the work inside of that gets hot, which makes the work inside that hot. So it heats from the outside in. So that's a big difference in the way they're heated and the way you have to think about them compared to a gas or a wood kiln.
But at the same time, because I was thinking about this earlier when you were talking about the heat sources coming from different places, aren't the ones on the outside then getting hotter than the big object in the center?
Yeah, the hottest thing in the kiln are the elements.
Right.
The hottest thing in the kiln. The elements are the hottest thing in the kiln.
Technically, are they firing to a different, what's in the center, would that end up firing to a different temperature than if you had a plate out here, then you had a heavier vase in the center?
The answer is yes. They are. Technically, they are. Because the ones on the outside are hotter longer. But this is, I'll get you just a second, but this is one reason why, for instance, you don't want to use glazes that are very specific with a narrow firing range, because then it's very possible to have the pot with that glaze overfired on the outside and perfect in the center of the because again, we do firing by cones, basically, which is time and temperature, right? Heat work. That's what we fire by, and that's what the clay and the glazes respond to. So it makes sense that a pot that's sitting on the outside of the shelf is seeing heat a lot longer than the pot in the center. So technically, that pot is getting more heat work than the one in the center. So if I have a glaze that's very specific firing, it can get overfired out here and be perfect in the center, or be perfect on the outside and be underfired. So that's a reason why you want to fire more slowly to allow the temperature to even out. And you want to have glazes that have a little bit of a range to them so that you don't see that difference.
I was going to share a story that you came over to help me with, because I've been firing really big flat pieces that also have a lot of complicated things in the middle with glass and things that have different issues that, so the corners were cracking. And Phil came over because I was getting really frustrated. And so now, I haven't fired a big one, because it's not something that you can really test fire, like with tiny little things, because the whole problem is it's big. So I'm just getting ready to fire another big one, and I built walls to go around the outside with a separate piece of clay to try to do exactly what he was saying you don't want to do with the big pot and the little pot. I actually want it to happen, because I need the center, the glass to...
Makes sense.
Yeah, because it's big and flat.
Yeah, yeah, and so whatever's closest to the elements is going to heat up first, and it's going to be heated longer. So, first, we're continuing with the small studio kilns. There are two types of power control that we have commonly: manual and automatic. And the manual are basically this, and this is what they when they first started out with electric kilns. You basically had on-off switches. This is a control panel from a really old electric kiln. This is a Crest kiln, and if you notice, it looks like it had 3 wall switches in it. Like that's what it had. It had switches that just turned an element on and off. It had three different rings, and you could turn 1 on, or 2 on, or 3 on, and that was the full. This is the complicated control panel. So the first ones were simply that. They'd have a series of rings, and when you wanted to turn the kiln on low, you'd turn 1 ring on, and when you wanted to get a little hotter, you'd turn 2 of the rings on, and when you wanted to get hotter, you'd turn 3 of the rings on, and that was all the control you had. And so when you think about that as well, okay, suppose I want to turn one ring on. Which one do I turn on first? The one on the top, the one in the middle, the one on the bottom? Because it's not going to heat uniformly, obviously. If I turn on the bottom one first, then the top's not going to get as hot and vice versa. So that was part of a problem with, you didn't get very uniform heating with this system, okay? But this was the earliest kind of control. So then these are just on-off switches. Then what they did, they developed a kind of switch that actually sort of had a built-in timer, and you'll see them, and they have like a range on them, and they're called variable or infinite. Actually, they call them infinite switches. But it goes to like not just, well, they also had ones that went like low, medium, high, and then they went to ones that were like 0 to 10 or different settings on them. And they basically had a built-in timing mechanism in it. So what it did was, when you turned it to a certain number, the power came on for a certain period of time and then turned off. So you'd hear, when you fired one of these kilns, you'd hear these things going bzz, 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 and every one of the switches was turning the power on, turning the power off, and they often would get out of sync. So you'd hear this constant sort of buzzing, turning on, turning off. And so when you turned it up to a higher setting, it let the power go to the element for a longer period of time. So if you were just turning it on low, it would kind of just click the power on, click the power off, just barely get them warm. And then as you turned it up to higher setting, and so you had this full range of settings where it would increase the time. And then finally, you could put them on high, and then the power stayed on to the elements all the time. So that was kind of the next step.
I remember because my first one was without kiln sitter or anything. It was
Yeah.
called Paragon, which you later got. And
Yeah, it's right outside here, by the way.
and you had to witness the whole thing. It was a gift, so what can I say?
Yeah.
And you did, and there was this wonderful little chart. It would say at hour 1, these peepholes in, turn this ring to this ring to this, and every hour you'd go in and remanipulate all of this stuff, and it was.
It worked. They work.
Yeah, and it gave beautiful finishes
Yeah.
still, but you're like,
Yeah.
when you go to digital, you never go back.
Now you just turn on the gas and let it fire.
But they still make manual kilns, and they work just fine. They work fine. But then they came up with the automatic or electronic controllers, and then they made them programmable. And the way these basically work, it works from the same principle, is that only now instead of having manual switches, there are electrically operated switches called relays that look like this. This is what's inside the control. That's a relay, which means that if I turn on an electrical circuit, if I turn a switch here, it tells this to turn on, and this turns on the power. So instead of turning a switch to turn on the power directly, this turns on the power to the elements. It relays the signal to the elements. It's called a relay. And so the way a programmable or the electronic controller works is there's a temperature measuring device or more of them in the kiln, and it measures the temperature. And the program, when they're calling it a program, it's a schedule. And in the memory of the little computer that's built into the kiln, there's a schedule that says, after an hour, I should be at this temperature. And after 2 hours, I should be at this temperature, that kind of thing, okay? So what it's doing is the temperature sensor measures the temperature and tells the controller, and the controller says, hey, it's a half an hour into the firing, I'm supposed to be at that temperature. Am I at that temperature? And if you are, fine. If I'm not at that temperature, it puts a little more heat into the elements. If it's too hot, it turns the elements off. And so the controller is trying to follow this preset schedule, which is basically time and temperature. At a certain time, I should be at a certain temperature, and I'm measuring the temperature constantly to see where I am with respect to that schedule. That's the way they work.
And so the new digital kiln?
Yeah. That's the way they work, basically. And so some of these kilns have a thermocouple, which is just a temperature measuring device that looks sort of like this. Thermocouple is called. And and sometimes they're in a little protective tube. This is a big one that sticks in. You'll see it sticking into the wall of the kiln. By the way, if you have a chance, if you're buying a kiln, get a kiln that has protection tubes and doesn't have bare thermocouples, because the thermocouples will last a lot longer. And this is like a car. The way they've made cars cheaper now is a lot of the things that used to get standard, now it's an option. And so, but if you want to it's one thing to look at is get a thing where your temperature measuring device is in a protective tube and not bare. It'll last longer.
There's a temperature offset though when you have that.
Well, there is with all of them anyway. There should be. Yeah. Which doesn't matter because you shouldn't be firing by temperature anyway. You should be firing by cones, which we'll talk about. Yeah.
Is there ever a shelf life on extra parts? Because that is the one thing I have learned from
No.
owning a kiln is buy all your extra parts.
Yeah, no, well,
If you're getting ready to buy one, buy extra parts, because if you're ever in a hurry and you don't have parts.
yeah, and most of the companies are pretty good as far as stocking parts, and there aren't that many. But if you want to have it on hand and you don't want to be out of commission for a while, then yeah. But anyway, that's the way the electronic controllers work. Is essentially it's still the same idea. Is that they're turning up the power to the elements and they're turning it up for a certain period of time. But the way they know how much to turn it up is what the temperature is compared to what they think it's supposed to be. So you can think of a firing schedule as kind of a graph, and this is in fact what they've got sort of built into the programmer. If this is temperature and this is time, a certain firing will look like that. And so they know that after 2 hours, I should be at that temperature. And so after 2 hours, the temperature that is recorded and goes to the controller, it compares that to this sort of list that it has. And it says, well, am I higher or lower or right on that temperature? If I'm higher than the temperature, it turns off the heat because I've overshot. If I'm lower than the temperature, it puts a little more heat into the elements. And if I'm right on, it just keeps on going. So it's constantly checking what time, what temperature am I? What time, what temperature am I? That's the way they work. And so an important part of these electronic controllers, if your temperature measuring device, your thermocouple, isn't working properly, the controller is useless. It's blind, basically.
And it will go to error.
Yeah, yeah.
So what's the optimal distance for a pot between the pot and the thermocouple? Because if it's really close or far away, it will measure.
At least an inch, I'd say, at least. I mean, I can talk about this later, but when I talk about loading. But one of the things I as a general rule, what I usually say is I don't have any pots hanging over my shelves. If you notice most shelves, you end up with maybe an inch or so between so you can get your fingers to load them. I just say I don't want any pots hanging over the shelf. And if you do that, then you're not too close. You're not too close to the wall. And I've seen studios where, because of either schools or like community studios where there's a lot of pressure to get pots through, and so they'll pack the pots into there, which and for bisque firing, it doesn't do a lot of harm. I mean, you can get away with it. But for glaze frying, if you pack them in too full, then you get differences, and you get underfired, overfired pots. So it's not worth doing it. One of the problems that I've seen, for instance, with bisque firings, and I've seen again studios where they just load the kiln up to trying to get the work through, is that some of the pots are over bisqued, some of the pots are under bisqued, and where that shows up is glazing. Because if you glaze, and let's say you're used to working with a certain glaze, you get almost a routine. Let's say you're dipping. You dip the pot, you get sort of almost a certain rhythm. You know that if you dip the pot into the glaze for a certain period of time, you're going to come out with a certain glaze thickness. Well, if the pot is under bisqued and you dip it in there for the same time, you're going to get a thicker glaze application because the pot is more porous. Or if it's over bisqued because it was close to the elements, you're not going to get enough glaze. So to me, when I'm firing things, I don't want to have to make a separate decision every time I glaze something as to how long do I need to hold it into the glaze. I wanted to get into this rhythm. And so the pots are reproducible if I don't overload the kiln. If you pack the kiln, then some pots are overfired, some pots are underfired. And then every pot is different in terms of what you need to do for glazing. So it just makes it easier.
So how full do you want to pack it when you do glaze firing?
Well, I mean, we're going to talk more about the later regime, but part of it is like you don't want it too close to the shelves. One thing to think about is narrow shelves that are close to space always heat up more slowly. So you want to think about where do you want to, if you have some short work, where do you want to put that stack of short shelves into the kiln? And there's some things that we'll talk about.
So this firing supposed to be 0.6 or 0.4?
It depends. As with a lot of ceramics, there's no simple answer to anything, okay? But the reason I say that is like, let's say you're firing to cone 10 or even to cone 6, you could bisque anywhere from 0.10, which is quite low, to higher temperatures like 0.6, 0.5, or 0.4. But what that's going to affect is like how much glaze gets absorbed when you, so a lot of that is what you want to do. There's no necessarily right and wrong thing to do it in a lot of cases. Like I found, for instance, porcelain, if you don't bisque it high enough, it's very fragile. And so if you bisque porcelain at 010, and it can be and you glaze, you can break the stuff just with glazing tongs or just handling it. So a lot of it might be the way you want to work. Like, what kind of consistency do you want your glazes? And how strong do you have to have the pots? Like, if they're very, very thin-walled pots, then you probably want to bisque them, differently than if they're thick. So a lot of it, in that case, there's no right or wrong. The other side of that is, if you're doing earthenware, which is low fire, then you probably want to bisque to 04. Because with earthenware, you want to bisque fire higher than you glaze fire.
So Phil, let me ask the question differently. What do you bisque do here?
I bisque to 06. For me, I found 06 is a nice compromise because it makes things, and regardless of what temperature I'm firing to, unless I'm doing earthenware. If I'm doing earthenware, I do 04. But for cone 6 or cone 10 or anything else, I bisque to 06 because I found it pretty much works for all types of clay, because different clays get stronger when you fire them than others. It works for just about any. So I found that's a nice compromise. 06. That answer your question? Okay.
Can you tell, last thing you said that with the thermocouples, there's like, it works like it's got a couple wires, so different materials in it. Can you explain a bit more about like how that works?
Yeah, the thermocouple consists of two metal wires of different compositions joined at one end. So if I have a wire and then a different kind of wire, and I join them together, and typically what I join them together by actually melting them together. I arc weld them together. This is called the bead or the junction. And so they're not just twisted together, they're really intimately connected. They're melted together. And this is the principle of physics, that if I have two metal wires of different compositions and I heat up the junction, it generates an electric current. It's bizarre, but it's true.
Is it like electrons jumping from like the metals?
Different levels, yeah. So just any two wires, metal wires of different composition connected together, when I heat up the connection, it generates an electric current. So if I stick, this is my thermocouple. So when I stick this joined wires into it and it gets hot, it sends back a very, very small electric current, and you measure the current. And the more current there is, the higher the temperature. And depending on what these wires are made out of, you get different amounts of current. So there's a whole different sort of set of tables, depending on what the pairs of wires are, that correlates to temperature. But you're measuring current, and that current represents a certain temperature. Which was a great discovery. I mean, it's bizarre though. You just connect two metals, heat them up, and you get an electric current out of it. Okay, let me keep going here. Okay, so programmable kilns we're still talking about. By the way, I'm not trying to discourage questions, but we had a long discussion at the beginning, and I don't want to keep people too late today. And I've got about another 37. No, I'm kidding. So we're good. And I want to allow more time for questions as we go along. So there are two. So talking more about the programmable controllers, there are two general types of programs that people do. One is called cone fire, and they may have different names, but the cone fire basically means that you pick on the controller, you select a cone that you want to go to, and you select the speed that you want to get there, and that's all you have to do. Really easy. So you might just say, and I think in general they're called cone fire. So you say, I want to do a cone 6 firing, and you'll put in cone 6, you'll put in 6, and then they'll give you a choice of either like fast or slow, or fast or medium or slow, and that's your heating rate. Now, what's interesting about this is that the companies, and so the kiln now knows, if I say cone 6 medium, that there's nothing standard about that, by the way. Medium might depend on the kiln company. What one company thinks is medium might be fast for another company, so you have to find out. But what they've done is, we talked about things are heated, or we fire by heat work. What they've done is the company has worked out for that particular size kiln, if I put this amount of power into the elements for 2 hours, they've worked out essentially how much heat work they're getting, and that's how they've worked out the schedules. So they've worked out the schedules, and they've calculated the heat work, the time and the temperature that you need to get to cone 6. And so that's essentially, and then they produce that in this form of the same kind of a chart, time and temperature, but they figured it out ahead of time. Okay. Now the other kind of firing you can do is called ramp and hold. And basically this is where you can write your own program. The other programs are canned. They're built right into the controller and you can't change them. But you can also do a program, like if you think of a heating schedule like this again, this is temperature and this is time. What you can do is you can break down, and I showed you this curve before that represents sort of the heating rate. You can break it down into small segments and you can write your own program for what you want those segments to be. So I can say that for the first segment, I can say, okay, I want the kiln to heat up to a certain temperature, whatever that is, and then I want it to stay there for a certain period of time, and that represents one segment. And so when you write these programs, they say you can create a certain number of segments that make up the program. So I can make up a program that essentially looks like this. And so in each one of these segments, I say how fast do I want it to heat up, what temperature do I want it to go to, and how long do I want it to stay there before it moves on. That's one segment. And typically the programs, depending on the manufacturer, will say you can write up to 8 segments or 10 segments or 12 segments, whatever they've allowed for in the program. And so you can build your own program. And you might be able to say, well, I'm doing a really weird firing and I don't want to fly right past a certain temperature. I want to go up to a certain temperature. I want to stay there for a while. And these canned programs won't do that. They're pretty much set to be kind of routine bisque firings or routine glaze firings. So this gives you the opportunity to write your own custom programs for sort of unusual applications. The other thing that this is really nice for is now I can do controlled coolings, because controlled cooling is really difficult with a manual kiln, because you can't, you can turn down some of the things, and then you have to watch the temperature, and and then if you get too cold too fast, you got to turn it back on. Well, I can just as easily program it to come down at a certain rate to a certain temperature and stay there for a while, and then down to at a certain rate to another temperature and stay there for a while. And then I can say, okay, now when I'm done, and now you can just cool off at the natural rate. So one of the things that controllers have really done is they've really popularized crystal glazes. These crystal, where you see these rosettes of crystals, because in order to develop the crystals, you have to do controlled cooling. So this has really made it easy to do crystal glazes now, because you don't have to manually try to guess on what the cooling rate is. You can set it. You can work it out and repeat it every single time. Yeah, Jane.
So with the digital kilns, because you can do that, can you also use it as a glass kiln? Mm-hmm. Because I know there's certain points.
Oh, absolutely.
You hold it and
absolutely. As a matter of fact, what's interesting is the kilns that we have here came with, in addition to the cone fire and the ramp hold thing, they came with 4 built-in glass programs, because they knew that you were probably going to want to do exactly that. So they have 4 programs built in for firing glass: a fusion, and a tacking, and a slumping.
And I fired in my kiln with glass and clay.
at the same time. Does the clay fume affect your glass or vice versa, or can you tell?
The fumes? Well, I probably don't get out of it. I don't know. No, I don't know. Maybe that's why I don't know. I've been there,
Yeah.
so. I don't know. But Phil's helped me because it's a challenge firing glass and clay because they have 2 different coefficients of expansion.
Exactly.
So it's been a little frustrating, but it's doable.
You like challenges.
As long as Phil's not the street. It's all an experiment.
We hope you're enjoying the show. Please take a moment to leave a 5-star review on your podcast platform of choice. It really helps new listeners find the show. Don't forget to subscribe to receive updates as new episodes are released. And if you'd like to support the video and podcast production of the Potter's Roundtable, become a patron. Go to patreon.com and search for The Potter's Roundtable. Your support will help us achieve our goal of creating a digital library spanning the ceramic arts for use by educators and artists alike. Thank you for your support. Now let's get back to the show.